Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem ID 3108, minimum cost walk in a weighted graph. This problem is based on a very good graph concept which is disjoint set union, or sometimes it is called union find algorithm. Also, this question has been asked in good companies like TShow and Amazon. It is marked as hard, but don't worry, like we will feel it as a medium problem if you know the DSU concept. Let's try to read the problem statement. There is an undirected weighted graph and vertices labeled from 0 to n-1. We are given integer n and array edges where array entries are in this form u to v w. Our graph edges are in this format. From u to v we have an edge and that edge is having a weight of w. But in this case it is an undirected graph. So we are also going to have edge from u to v to u. Like this arrow is bidirectional, u to v and v to u. And after that they are saying a walk in a graph is a sequence of vertices and edges. The walk start and end with a vertex and each edge connects the vertex that comes before it. And the vertex that comes after it, it's important to note that a walk may visit the same edge and vertex more than once. They are just defining some kind of walk. Walk means like just walking over a couple of nodes and the edges definitely. And what is the cost? Cost of walk starting node u and ending node v is defined as the bitwise AND of weights of all the edges traversed during the walk. Bitwise AND of all the edges over that walk. If on the walk we have k number of edges from 0 to k, then this is the cost. We are also given a 2D array query, and for every query is source to target. For every query just find the minimum cost of the walk. So for every query we have to find the minimum cost as well. So this is the lengthy statement. Let me just explain it to you in simple words. First of all, what is given to us? We are given a n. N is the number of vertices which are from 0 to n-1. Apart from that, we are also given edges. Edges are in this format u to v, and this is the weight of edge, and this edge is undirectional. So if we are picking the first edge, it means there is an edge from 0 to 1 and 1 to 0, and the weight of that edge is 7 for both. So this is how the graph is given to us. Sometimes we are in the form of edges and the nodes. Apart from that, the third point is query array. In this query array, every query is starting vertex and ending vertex, and from starting vertex till the ending vertex, what can be the minimum cost of the walk? That is, we have to capture. And this is our operation. Find the minimum cost for every query. For every query, you understand what is query, starting and ending, and finding minimum cost. Minimum word you understand. What is cost? Cost is AND, bitwise AND value of every node at every edge, weight at that path, right? So what is the cost? Cost is, let's say this is the node count, and this cost is 7, this cost is 6, and we are starting from 1 and ending till 3. So the walk has a cost of 7, bitwise and 6. So this is the cost, right? So this is given to us, and what we have to return is for every query we have to return the minimum cost against every query. So this is our problem statement. And now first of all, let's see what is this graph. 0 1 7. 0 and 1 is connected with the value 7. 0 1 is connected, it's a bidirectional edge. I am not putting arrow, and the weight of this edge is 7. 1 3 is connected with weight 7. Apart from that, 1 2 is connected with weight 1. So this is the graph. In this graph you can comfortably see that okay, we have two components in our graph, and now the graph representation is done. And from this graph, what we have to figure out is we will be given a query. Let's say just pick the first query. First query is 0, 3. So we have to start from 0 and go till 3. And what we have to figure out is minimum cost over that path. And cost is and bitwise and of all the edges over that walk. So if I just directly go from 0 to 3 by this path, what will be the value of and? 7 and 7, which is 7. And if I just go to above and then come here and then go back and then come there, in that case, can we go like this? In the problem, it is already given that we can visit the same vertex or edge more than once. It doesn't matter how long you, like how much nodes you are encountering in this walk, how much edges you are using in that walk. It doesn't matter. You have to start from start and reach the end and just get me the minimum value of and among all the roots, right? So in this case, this was the first one path, 7 and 7, and the second one was 7 and 1 and 7. What is the binary representation of 7? 1 1 1, 0 0 1, and is for 0, and 1 1 is also 7, so there is no need to take it twice. So what is the end of all of these? 0 0 1. In this case, if I just start from 0 and then go to edge 1, go to edge 2, go back to edge 1 again, and then go to 3, in this case my cost is 1. So here the minimum cost is the answer. So answer to this query is 1, right? So this is something we have to figure out. This was for the first query, and second query is 3, 4. 3, 4. Let's try to figure out the answer for 3, 4 as well. See, do we really need to check for these two vertices? Because 3 is in this component and 4 is in a different component. If they are in a different component, it means there is no walk between them. If there is no walk, then the answer is -1. Here in this case, answer is -1. Now what we understood here is, we got the clarity that if the query u, not u and v, start and end, if they are both from the same component, then we have some value. Else part is -1 always. So if they are from different component, then it is always a -1. What does the different component means? In DSU, in disjoint set union, they are having different parent. So this concept we are going to revise again. Just be with me. And so yeah, if it is a different component, -1 is the answer. If the same component, then what is the answer? Here if you try to analyze that, we can visit any node or any vertex, any edge, any number of time. So it doesn't matter how much part do you take. If you go to 2 again, then there is no issue. But yeah, if you are taking and with something else, let's say this is the 7 is the cost I am having right now. If I am taking and with any other number, if we are encountering 1 at the same places, then we are getting 1, otherwise 0. So definitely the value is less than equal to 7, right? If you are taking and with something, definitely the value is going to be reduced or the same or the reduced. So if just taking and with something else, let's say first edge is 7. If I am taking and with something, the resultant value will be less than equal to 7. If taking and with any other edge weight, I'm getting some better result. So why not you just take and of everything? So what I'm trying to say is that taking and of every single edge within that component is going to give me the minimum and. So in this case, what is the minimum and? From starting from 0 to 3, first step is the same component. If they are same component, then I will move further, otherwise -1. So if it is the same component, then what I will do is and nodes, not nodes exactly, of all weights from all of the edges, and operator of all the weights from all of these edges. Let me clean a bit. So here we got two cases. If the starting and the ending are from the same component, then taking the end of all the weights are going to give me the minimum cost. Otherwise, second option is if they are from different component, then definitely the answer is -1. So these are the two categories for our queries, and we are getting an idea that we somehow need to keep track of the connected components. And to keep track of the connected components, we have a very good data structure, that is disjoint set union. And for the bitwise AND, we got the intuition that okay, if we are taking AND with something else, we are definitely getting a lesser value, because taking 7 AND with 7, I'm getting 7. Apart from 7, if I choose anything else, I might get less than 7. So after this, what I would require you to understand is disjoint set union data structure. And if you are not comfortable with disjoint set union data structure, I have prepared a dedicated video where I have covered this topic in detail. You can just have a look. I'm going to attach the video in the description below. And if you somehow feel you are a bit comfortable with DSU, then let's try to prepare the DSU for this example. Take it as a revision. In disjoint set union, first of all, we should have a array and to keep track of the parent of every node. First of all, I am taking a parent array. In this case, we are having 5 nodes going from 0 to n-1, and those nodes I can easily mention with the array, because array indices are in this format: 1 2 3 4, 0 1 2 3 4. So this array is going to store the parent of every single node. Initially, every node is a parent of itself. The nodes are something like this: 0 1 2 3 and 4. Nodes are like this. No two nodes are connected. Every node itself is a parent, and to represent that, we require -1. -1 means that the current node is the parent of itself. So right now we are having 5 components, right? We can say that because we have 5 components, and slowly we are having an edges. These edges are going to create those connected components. These nodes, edges might connect 2 components into one, or they just belong to the same component again. So in this case, if every component is a single component, if I just add one edge, so that edge is going to reduce the total number of components, and that might reduce from 5 to 4. Okay, so initially this is the first step, creating a parent array. In this parent array, every element is initialized with its parents. Parent is the same. Now if I just try to use the first edge means connect the 0 and 1. Connect the 0 and 1. And I don't do it directly. What I do is find the parent of 0 and then find the parent of 1, parent of A, let's say parent of B. Then what I do is parent of A is equal to parent of B. I just connected those 2 components. This is a union operation. So here, firstly try to figure out the parent of 0. Parent of 0 is -1. -1 means 0 itself is the parent. So parent of 0 is 0 and parent of 1 is 1. 1 itself is the parent. Now what you will do is parent of A will become the parent of B now. So parent of A is 0. 0 will become the new parent of B. B is 1. So 1 have a new parent which is 0, and 0 itself has a parent of 0. Now this edge is connected. In this case, if you just try to have a look, and this introduction of one edge is reducing one component out of it. 0 and 1 have a parent equal to 0, and 2 have a parent of 2, 3 has a parent of 3, 4 has a parent of 4. So now we are having 1 2 3 4 groups, and this small little new group is having parent of 0. This is a union operation, and in this union operation itself, what I am doing is I am just calling one find operation, which is finding the parent. Finding the parent means like finding the parent in this parent array. So that is our find operation, union and find. Sometimes it is called union and find. But I highly recommend you to go and watch this video. In this video, it's a detailed explanation, but this is just a revision. Now just try to cover up all the edges. Second edge is 1 to 3. Connect 1 and 3. If I connect 1 and 3, what is the parent of 1? Parent of 1 is 0. Parent of 3 is 3 itself. Now 3 will become the parent of this B. Right? So this is the parent of 0 and parent of 3 is 3. So parent of 3 will be updated to this parent because we are merging these two in the same component. So 3 have a new parent which is 0. Now this is the state. What is the third edge? Third edge is connect 1 and 2. What is the parent of 1? That is 0. What is the parent of 2? Which is 2 itself. Parent of 1 will become the parent of 2 as well. That is 1 and 2 we are connecting, and 1 has a parent of 0. 2 will also have a parent of 0. In this case, we'll be updating like this. So here if you try to have a look, 0, 1, 2, 3 are from the same component because it has a parent which is equal to 0. 0 is the parent, and here parent is 4. So these are the two connected components which we formed using this parent array, using disjoint set union. Correct? Now we have the component, and now if we just tackle the queries, let's say queries in this form. This is the starting and this is the ending. Starting, ending. Firstly find the parent of starting. So to find the parent we have a function which is find. So find A and find B. If they are not equal, just directly return -1. If they are equal, then do something. What you are going to do in that case? It means they are from the same component. If they are from the same component, let's say from the first component, whatever two elements are there, 0 to 3, from 0 to 3, whatever two elements are there, what is the minimum cost? Minimum cost is visiting or taking AND from every single edge in this component. In this component, the weight was from 0 to 1, with the weight is 7. From 1 to 3, the weight is 7. 1 to 2, the weight is 1, and this is 0. So if 0, 3, they both belong to the same component, just take AND of every single edge. 7 and 1. This will be the answer. If they are from different component, then -1 is the answer. And ultimately you have to return the answer array. Now how can you do this operation in efficient manner? How we can do that? See, if from the parent array we get to know what is the parent. For first 4 element, the parent is 0, and for the fourth the parent is 4. Okay, ultimately we have 2 parents, 2 groups you can say. So whatever edge is going to fall in this component, like whatever edge, for whatever edge means like edge is starting from any node. Edge is always in this format, U to V. Let's say we are picking U, and U have a edge associated with this. Let's say 0 has an edge of 7 associated with this. So if I just find the parent of U, find U, this is the parent of 0 in this case. Parent of 0 is 0. What I'm saying is find the parent of U, and parent of U is like the component ID. Component ID you can consider it. So for that component, the contribution of the weight will go to that component only. So for every component, let's say the component ID maximum it can go till n. But here in this case, this is only 2 components. 0 component starting with component have a parent of 0, component have a parent of 1, and component with the parent of 0, whatever edge is falling in that, just take AND of those edges. Just take AND of all the edges where the node is where the U is following in that, where U has a parent of 4. Got it? And this will be the answer if two nodes, let's say A and B, are following in this group. So this is ultimately the approach. The approach is disjoint set union, DSU. Using DSU, first of all, step 1 is creating components and then checking whether those components belong to the same group and different group. First of all, we are going to create the components out of our graph, like capturing all the components, and then we will decide for every query from starting to ending if starting and ending are belonging to the same component or different component. If different component, return -1 directly. If same component, whatever, let's say this is the component they are belonging to, whatever is the AND of all the edges, that is our answer. So you just have to code this approach. So here it is clear that we are going to use DSU, disjoint set union, and for that the most important thing is having a parent array. This parent array, we have to keep it in the class itself, class member, so that it can be accessed among the functions. And we should be having two functions. First one is find and union. What is this parent? Let's initialize this first. Parent is equal to new integer array of size n, and this arrays dot fill parent with -1. -1 means every element is the parent of itself. We have n vertices, we have n components in our graph, as we have not processed any edge. Now we have to implement find and union function. Public finding is going to return integer, and then it's going to take a value. Let's say it is finding the parent of x, and union is let's not return anything. Union is making two disjoint set combined. First disjoint set is the disjoint set with the parent equal to the parent of A, parent of B. If they are having different parent, they are from different sets. If they are having same parent, they are already connected. So first of all, find the parent of A, find the parent of B, and this find operation is something we have to implement if the parent of x is equal to -1. In that case, return x itself. X is the parent. Otherwise, what we have to return is find of parent of x. And let me do something here. Parent of x is equal to find of parent of x. What I am doing here is, this is called path compression, some kind of pruning. So these two functions we have to use for our approach. Now let's implement this union operation. Find A, find B, int parent of A, int parent of B. If parent of A is not equal to parent of B, we have to do the union. Otherwise, no need to do anything. Parent of A is the parent of B. Now we have the parent of both the groups, and now this parent of the first group will now be the parent of second group. So parent of parent B is now the parent A. Now the two disjoint sets are combined. This much we have to use here. I think disjoint set is sufficient. I have initialized the disjoint set, and after that, to fill the connected components, to prepare the connected components, we have to process all the edges. So for every edge, make the union of both the element edge of 0 u and v edge of 1. So I have combined two components. So just do the union of this, and apart from that, Apart from that, we will be maintaining some kind of map, where map is going to have the parent of that component, connected component, with the cost of that component. See, we have discussed in our discussion that every connected component is going to have a cost. See, let's say in this case we have two connected component. This left side connected component have a cost of 1 and the right side have a cost of 4. And if two vertices starting and ending fall in this first connected component, they are going to have the same result every time. So parent and cost, and for that we have to maintain component cost. And component cost is going to have a parent to cost mapping, and parent can lie from 0 to n-1. So let's take the same size integer array component cost is equal to new integer of size n. And this cost, and what is this cost initially? Initially the cost is, what should I initialize it? See, in that case, if we are taking AND with so many numbers, so what should be the identity of AND? If you are taking AND with all the ones, you are getting the same number. If you are taking 7 and all the numbers, you are going to get 7. And what is this all the numbers? Equal to 1. This is plus infinity. So arrays dot fill component cost comma integer dot max value. Integer dot max value. So this max value, we have initialized our components, all the components. Now we have to move to our edges again so that we can process the weights. For every edge, let's say every edge is going from u to v. So whatever edge is connected to u, we have to find the parent of u and make the AND in that value. So for every edge, edge into edges, what I have to figure out is edges from u to v. First of all, we have to find the parent of u, and that will be the index for the current component cost. So parent means find operation on edge 0. So this is the parent, and what I have to do is component cost of parent and equal to whatever is the cost. Weight is 2, correct? Component cost of parent, the edge is u to v, and u belong to which group? This group with the parent equal to this value. And for this group, the cost, I have just did the AND, because we have decided that for any connected component I have to take the AND value of every single weight, every single edge. So this after this operation, we have our component cost ready. Component cost means whatever is the parent, if two starting and ending. For every, let's say if every query is something like this, start and end. For this query, I'll just find the parent of start, parent of end. If the parents are different, then -1 is the answer. There is no answer, these are not connected. If they are connected, then AND value of that component cost just over one time. Now process every single query. For integer array, the given is query is given, so let's call it q query. In this query, like first of all we have to find the parent of start. Int parent of start is equal to find query of 0. Int parent of and starting and ending, let's say parent of ending is equal to find the query of 1. So this is the parent and like parent of starting and parent of ending. If parent of starting is not equal to parent of ending, what is the answer? Answer is -1. And how do we have to return the answer? So answer of I is equal to -1. What is this I? I need to take a variable array to store my answer. New integer array of size query dot length, and what is the value of I? Int I equal to 0, and in this iteration I will be incremented, and answer of I is equal to -1. Apart from that, what is the else case? When both the parents are same. If both the parents are same, what is the answer? At I is equal to component cost of parent of anyone, parent of starting and parent of ending, both are same, so whatever is the value, just that is the cost, and that is the cost for the ith query. In the end, return answer. Let's have a quick review. Firstly, we are utilizing DSU concept. I have not utilized the ranking in union operation because I don't like doing that. That is, this one is sufficient path compression. Union, okay, this one is done. Minimum cost, DSU is initialized. Union of all the on all the edges. It means that we have the disjoint sets now, connected components now. After that, I'm taking a map, you can say, or integer array where it is something like parent and the cost. Cost is, what is cost? And of all weights in that connected component. This one we did, and then after edge, this is something we processed. And for every query what I have to figure out is just check the value in connected component cost. Let's run our sample test cases. Sample test cases are passed, luckily passed in the first go, and let me submit the problem. It got submitted successfully, and I hope you understood the approach. Also, do watch that disjoint set conceptual video. That is more important than this solving this question directly. And what is the time complexity for this? Time complexity is we are covering up all the edges. All the edges are, let's say, E in number. E. We usually have vertices and then edges. We are processing our edges, and edges are E in number. But along with that edge, what is the cost for the query? Time for the query. For every query we are spending order of 1 time, and let's say we are having m number of queries, and that m value is way larger than the number of edges. So in that case, what you can call it, overall it is the time of E plus Q, number of queries, or let's say m number of queries, where m number of queries we are having. So this can be our time complexity. Okay guys, thank you, bye bye.